This is lesson 4.7 on logarithmic functions. So we introduced logarithms in the previous section and said that we can think of them as basically exponential functions or exponential problems in reverse. So if we make this silly little observation, log base a of a to the b, if we were asked to evaluate that, again, what we would have to ask ourselves is, okay, a raised to what power equals a to the bth power? Well, that's kind of a silly question, isn't it? It's obviously going to be b. So this kind of duh statement actually leads to a pretty important revelation. Notice that we have the composition of two different kinds of functions, a logarithmic function and an exponential function, and they each undo the other. We've seen this idea before. That is exactly what inverse functions do. So, not really a surprise to us, but we finally see that logarithms and exponential functions are inverses of each other. They're each going to undo the other. Now, what this means then is that if we want to look at the graph of a logarithmic function, all we need to do is take the graph of an exponential function and reflect it across the line y equals x. So one thing to note is that remember that our exponential functions had a horizontal asymptote. When we reflect that horizontal asymptote across the line y equals x, it's going to become a vertical asymptote. So horizontal asymptotes from our exponential functions will become vertical asymptotes for the corresponding logarithmic function. Now, just to remind ourselves, these are what the graphs of our exponential functions look like. So these are the graphs of y equals a to the x, where on the left our base a is bigger than 1, and on the right our a is between 0 and 1. If we throw in our line of symmetry, so y equals x, the line that we're going to reflect about, we can see that the graph of the logarithmic function is going to be written here. So here we have our exponential functions in blue and our logarithmic functions in red. So on the left, we see our usual exponential graph when a is bigger than 1. When we reflect it about the line y equals x, that gives us the graph of log base a of x, where again that a is bigger than 1. So notice that our horizontal asymptote of y equals 0 becomes the vertical asymptote x equals 0. Furthermore, an important thing to note, remember, when we switch from a function to its inverse, the domains and range flip-flop. So before, the domain of our exponential function was all real numbers, and the range was everything bigger than 0. So now things flip-flop. The domain of logarithms is everything bigger than 0, and its range is going to be all real numbers. For the other graph, when we have a between 0 and 1, picture looks different, but the overall story is the exact same. Our horizontal asymptote becomes a vertical asymptote, and our domains and ranges switch places. So when we take away the exponential functions, we see what the base logarithmic functions are going to look like. Now, if you're like me, I sometimes kind of trip up on this and don't remember my logarithmic graphs very well. Worst case scenario, if you forget which way is which, but you remember what the exponential graphs look like, go ahead and sketch the exponential graph real quick, reflect it about the y equals x line, and that will show you what the logarithmic graph would look like. That's not ideal. Ideally, you should have these memorized. But worst case scenario, you can do things this way. So we're going to be looking at graphs of logarithms. We're also going to look at a word problem where we're going to use this property of logarithms, the fact that logarithms and exponential functions are inverses, to solve a particular kind of word problem. Okay, so we're asked to sketch the graph of y equals log base 3 of x plus 2. So the very first thing to do is to focus on the base logarithm here. Notice that we have a base bigger than 1. So we know then that the base graph is going to look like this. Remember, we're always going to have a vertical asymptote along the y-axis. If this is bigger than 1, We're going to be going down for the vertical asymptote. If it's between 0 and 1, we'll be going up. So in this case, our graph looks like this. This plus 2, it's outside of the function, it's outside the logarithm, so this is going to be affecting our vertical direction. So we're going to shift this up by 2. So here I would just indicate that we kind of stay very small before actually shooting to the right. So I would say we still have a vertical asymptote, of course, but maybe draw it kind of like this. See how we start the asymptote a little bit sooner. So this would be perfectly fine. Take this graph, shift it up by 2 a little bit, shift it up some. This indicates that we have done that. We continue to have fairly small x values in some sense as our y value increases here. So base graph, shifted up by 2 is going to look something like this. Here's another one. So sketch the graph of y equals log base 1/5 of negative x. So once again, let's just focus on what is the base graph. So what does y equals log base 1/5 of x look like? So here our base is between 0 and 1. So this time we know that with our vertical asymptote we're going to be going up. So our base graph looks something like this. So this is the graph of y equals log base 1/5 of x. This negative, it is inside the function, so it's going to be affecting our graph in the horizontal direction. So this negative means that it's going to be a reflection. It'll be a reflection about the y-axis. That's how we reflect it in the horizontal direction. So if we take this exact same graph, but reflect it across the y-axis, it will look like this. So there we go. There we go. All right, so let's consider this word problem. So when we're looking at this word problem, hopefully it seems somewhat familiar. It looks very similar to the compound interest problems that we saw a few sections back. In fact, we are going to use the continuously compound interest formula to solve this, but we're going to see that we're not going to get our final answer in quite the same way that we did in the previous problems. This requires the use of logarithms. So here we've got Benjamin, who's investing $1,000 into an account that continuously compounds interest. He's wanting to retire on this. He's wanting it to earn $1 million. So we're wanting to find how long it's going to take for that to occur. So our continuously compounded interest formula, remember, is A equals PE to the RT. So A is the amount that we want to have, P is the principal, the amount that we initially invest, R is the annual interest rate, and T is going to be the number of years. So in this case, T is what we're wanting to solve for. So the amount that we want to have is $1 million. So $1 million equals our principal. We initially invest $1,000 times E to the RT. So our interest rate is 5%. So remember to put that in as a decimal, 0.05 times T. T is what we're trying to find, so just leave it as T. Okay, we want to get this E completely by itself. So let's divide both sides by 1,000. So when we do that, we're left with 1,000 on the left-hand side and E to the 0.05 T on the right. Okay. So here's where the magic happens. We have E here. The variable that we're wanting to solve for is stuck inside the exponent of E. So how do we undo an exponential function? We take a logarithm. So what we're going to do is let's take the logarithm of both sides of these, the natural log. We want to use the base log that has the same base as the base of the exponent. So natural log of 1,000 will have to equal natural log of E to the 0.05. 0.05 T, I should say. All right. Let's make our observation that we saw before. Natural log of this is saying, all right, E to what power gives me E to the power of 0.05 T? Remember, natural log is log base E. So E to what power gives me E to the 0.05 T power? Well, obviously it's 0.05t. All right, now e to what power equals 1,000? Well, obviously that's going to be 6.908. I'm just kidding. We got that from the calculator. You would need to put that in a calculator. There's no way we can get that very easily. All right, so 6.908 equals 0.05t. This is just a nice linear equation at this point. Divide both sides by 0.05, and we get 138.16. So I don't know how to break it to Benjamin, but I think you might need to look into something else. This is not going to work out too well for him.